So the example that you see here is one that we've looked at before. Let's take another look at it though, now that we have a bit more modeling capability. The above table gives the annual sales of cassette tapes in the United States for various years between 1994 and 2001. Earlier, we found that the best fitting linear model for this data was the following. Now we want to find the best fitting exponential model for annual sales in millions of cassettes as a function of t, the number of years after 1994. And then we'll calculate some more quantities here. Okay, so the first thing that we need to do is enter this data into the stat editor. But remember that this is an elapsed time model. It says the number of years after. So 1994 is going to be year 0. 95 is year 1, and then 97 is year 3, because that's 3 years after 94. 2000, that's year 6, and 2001 is year 7. So this is actually going to be our L1, and then L2 will be these values. So I'm going to enter these values off camera. So as you can see here, I've now entered this data into the stat editor. So I've got my L1 column is Z01367, and then my L2 column are the tape sales. So again, we have this precipitous drop in sales for tapes, which is expected since this is happening during the years when other media formats were introduced, like CDs and so forth. So we want to find the best fitting exponential model for this. So we're going to do exponential regression. So we go to stat calc. 0 is xpareg, and then my calculator has this interface. And so there's our model. 365.51 times 0.76 to the t, rounded. The parts B and C of the model, we want to find the SSE, the average error, the correlation coefficient, and then talk about the model a bit. So to find the SSE, we do this the same way as we did the linear function. That's sum resid squared. So we go to second stat, math, choose number 5. Then we return to second stat, and then under names, we have 7, which is resid. And then make sure you square that, hit enter, and that's our SSE, 745.34. And that's in millions squared, right? That's our unit for the SSE, is millions squared. So notice that we've actually the SSE for exponential is much lower than the SSE for the linear fit, which is better. Basically, this is much better. For the average error, we have 1, 2, 3, 4, 5 data points. So we're just going to take the square root of the answer divided by 5. And our average error is 12.21. Again, much improved over our previous average error. That's a 12.21. And then for the correlation coefficient, we go to vars, statistics, equation, number 7, and we have, notice that it's negative, but that shouldn't be a surprise if you think about what we're modeling here, because we have decreasing behavior, right? This is a decreasing sales distribution here. So that would be negative correlation rather than positive correlation. But that's still good. I mean, this is pretty high. And I think if we compare this with the associated critical value for 95% confidence, we will definitely exceed it. So we can be pretty sure that we're 95%. Or sorry, we can. I am 95% confident that if we look up the critical value, we would indeed be 95% confident that our correlation coefficient the absolute value of our correlation coefficient exceeds the critical value. Okay, that was a bit of a mouthful, but I'll write that number down. Negative 0.9929. Okay. Actually, that was 3 because it had a 7 there. All right. In terms of the exponential model's growth rate, let me return to that. We haven't actually identified the growth rate, but the model, let me scroll back up here. It's not letting me. Anyway, the model, to get the growth, how do we get the growth rate? We go to VAR's statistics equation, and we can't directly call up the growth rate. What we can call up is the factor. And then if I subtract 1 from the factor and multiply that by 100, that is my growth rate, 24.44%. And it's negative because it's not actually growing. So what this is saying is that every year we are decreasing by 24.44% our sales, which is pretty bad if you're a cassette tape salesperson. Okay. So here's our official answers. Now, I was kind of bumbling around talking about the critical value, but here's the actual computation. The critical value for 5 data points is 0.878. Our correlation coefficient was negative 0.993, and its absolute value certainly is larger than 0.878, so we can indeed be 95% confident that there's correlation, and in fact negative correlation. In terms of comparing this to the linear model, it's the exponential model in this case is better in practically every way, in the correlation coefficient, in the SSE, and the average error. So there's no doubt that the exponential model is a better fit than the linear model. Of course, that's not always true. It's just true in this case. Okay, so this next example that we're going to look at is, it is related to exponential modeling, definitely, but this is actually a little bit different than the kind of problems we've been doing up to now. And these problems that are all about things heating and cooling are all going to be in their own section. Okay. So this is, as I was saying, this is a new type of problem, and this is actually going to be the beginning of 5.3b. So I'm going to stop this video here, and we'll start a new video that will be just for section 5.3b.